So welcome everybody. This is the first talk in our webinar series 2021 of the Language Technology and Data Analysis Lab, LADAL. My name is Martin Schweinberger. I'm lecturer in applied linguistics at the University of Queensland and associate professor or professor too at the Arctic University of Norway in Tromsø. I have a background in English linguistics and I focus on computational processing and statistical modeling of language data. And I'm also very interested in reproducibility in the language sciences. So as of now, I'm co-director of LADAL with Michael Hoare, who is professor of linguistics and applied linguistics at the School of Languages and Cultures at the University of Queensland. He's an outstanding figure in pragmatics, intercultural communication, and human studies. He's co-editor, co-director of the LADAL, and he's also a leading proponent of the Australian text analytics platform ATAP and the Language Data Commons of Australia, LADACA, which is co-investment of the ARDC in Australia. Before we start, I'd like to read out an acknowledgement of country. So the University of Queensland acknowledges the traditional owners and their custodianship of the lands on which we meet. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognize their valuable contributions to Australian and global society. Before I introduce our speaker, Stefan Gries, I'd just like to ask you to switch off your cameras when you enter and to switch off your mics. We'll have a Q&A session after the talk. And if you have any questions, feel free to post them in the chat. Today's presentation is by Stefan Thomas Gries, and the presentation is on multifactorial prediction and deviation analysis using regression and random forests. Stefan is full professor at the University of California, Santa Barbara, UCSB, as well as honorary Liebig professor and chair of English linguistics at the Justus Liebig Universität Gießen. He has held several prestigious professorships at top universities, for example, Stanford and Max Planck Institutes. Methodologically, he is a quantitative corpus linguist at the intersection of corpus linguistics, cognitive linguistics, and computational linguistics. He has applied a variety of different statistical methods to investigate a wide range of linguistic topics, and much of his work involves the open source software R, which is a fantastic programming environment. He has produced more than 200 publications, so he's very, very productive. And he also has brought many linguists into contact with quantitative analysis. So I'll hand over to Stefan, if that's possible.
I certainly hope so. Let me share the screen.
Stefan,
yes.
Can you make yourself a little louder, maybe?
Yes, I'll try. I was just changing the volume of the microphone. Is this working better?
Now it's good.
Now it's good? Okay. All right. So thank you very much for the invitation and for the kind introduction. I'm very happy to be here and talk a little bit about this MuPDARF method, and I want to do so by way of well, a longish introduction that also involves a brief review of sort of traditional learner corpus research, which I will use a little bit here as a springboard, criticizing some of the earlier traditional work that has been done to then basically move over to the kind of methodological approach that I want to sort of advertise or promote or introduce here. Okay, so as you can see, there's ultimately going to be a handout, which is what you see here on the screen. So that's going to be a downloadable version of this HTML file together with the data file that we'll be looking at here, so that ultimately, you'll be able to rerun the whole analysis. And as you can see, this is kind of like a book chapter or something like this. So it's a markdown, obviously a markdown document knitted to HTML that generates all the code, all the results, and it's pretty long. So we'll have quite a lot of stuff to go through because apart from this MuPDARF introduction, I also want to talk a little bit about how I think if one uses random forests, they should be used in this kind of setting. So there's also going to be a little bit of a statistical intro to tree-based approaches and how they should be properly done at the end of it. So it's going to be quite long. And at the end of the session, once I'm done, I'll let you know where the download location is so that you can get a zip file that contains all this stuff. Just to preempt the question already, why isn't he giving us this in advance? Because my experience is that no one listens to what I'm saying anymore, and everybody is just going through that thing at their own pace, and I want to avoid that. So that's why you only get this at the end. All right, so as you see, the title is Motivation, Practice, and Thoughts on Extension of MuPDARF. And so I want to start very briefly by mentioning the main phenomenon that we're going to be looking at that's going to serve as the backdrop for everything we talk about here. And the phenomenon we're going to use is this omission or realization of an optional complementizer that in a reduced version of a data set that was used in the publication before. So we're only going to be looking at that in object and subject complementation by native and non-native speakers of English, with the L1s of German and Spanish for the learners. Okay, and so crucially here, you should look at this for a brief second. This is a case in point. Okay, so a sentence like, seriously, I really hope very much that, or not that. Okay, so that's the critical alternation here. The Vorlons will help us against the shadows. And the question is, what are the factors that determine whether that will be inserted there or not? And at the same time, how do learners, if they differ, how do they differ from native speakers in that regard? And I mean, the sentence obviously is a little bit awkward, but that is because I inserted all sorts of material there that might not normally be there, but that will help us understand some of the predictors that are involved there. So let me tell you that already. So it's going to be critical to see whether there's material before the main clause, in the main clause, between the subject and the verb, after the verb, before the that, and so on. Okay, so that's why the sentence has this slightly weird context. Now, to introduce the motivation for MuPDARF, we need to look briefly at how traditional learner corpus research might have looked at this. Okay, and this is going to get a little ugly, but again, I mean, one needs to show, I think, why, what the state of the art was for a very long time in order to understand why I think this kind of approach here has something to offer. And so if we take a traditional learner corpus research perspective, around the 1980s, like from between the 80s to the aughts roughly, who wanted to look at this phenomenon, then a lot of the traditional LCR work used two theoretical frameworks that I don't want to comment on much. Fine, those are not the point here. So one would be contrastive interlanguage analysis, and the other one the integrated contrastive model. And I talk a little bit about here what characterizes those. The critical thing is this, namely that traditional LCR, as characterized by the adoption of these two frameworks, basically made two methodological choices. And one is, the linguistic element to target, obviously. So that's going to be the that versus not that realization here. But then the other one is less duh, namely the quantitative resolution that we adopt here. Okay, and it's probably fair to say that for quite a long time, this traditional LCR approach was characterized by this notion of overuse and underuse. Okay, so what one would do is one would compare frequencies that are attested in corpus data and would run a chi-square test or a log likelihood test on them, or some similar kind of test reviewed in Paco and Blonsky to see, is there a significant over or underuse by the learners such that, even if something is not outright ungrammatical, it's still not representative, so to speak, or not compatible with the probabilistic distribution we would see in native speaker data. And so here, give a few examples. And so now let's see what that would look like, if we actually did this. And so here's a small part of the data set we're actually going to look at. Okay, reduced to what in a traditional LCR work often was done. Namely, we have the dependent variable, whether the complementizer is used or not. And then we have as a predictor of sorts, the L1 of the speakers, right, from some corpus data. And so how would that normally be done? Well, in R, it would look something like this. We might generate a table where we cross-tabulate the three L1s, the native one and the two non-native ones with the two levels of the dependent variable. We might compute some row percentages, which are already, well, insightful to a certain degree, in the sense that we see, for instance, that the native speakers more often than not, by a factor of 2 to 1, or a ratio of 2 to 1, do not realize the that. Whereas for the German and the Spanish learners, it's more like a 50-50 distribution. Okay, and then often we get like some per million word frequencies or something like this, and then we get some statistical test, often a chi-square test or a log likelihood ratio test. Now, first problem, it's actually often, from the description, it's actually often pretty much unclear what actually was done statistically, I'm sorry to say. So here's an example from a study that did something, well, I don't know what they did actually, but they theoretically did something somewhat similar. We have the frequency of a certain word for learner varieties, and then some native speaker data. We have some relativized frequencies. And then what they say is that they report, there are differences that have certain significance levels, blah, blah, blah. And then the frequencies were compared using chi-square. And honestly, I have no idea what that means. I try to replicate this, but I don't know whether they did a chi-square test for goodness of fit or a chi-square test for independence. You don't know whether it was done with some continuity correction or something like this. It's just not clear. Okay, this is not to mention that a chi-square test is not even a good idea here, but even trying just to replicate this a lot of times would not work out well. Here is another case that is pretty typical of a lot of what's done. So here we have a table, native speakers versus non-native speakers, and the frequency of combinations of verbs and nouns that are collocations versus non-collocations. And then there's a variety of things reported here where I don't even know what those are. I mean, I don't know this statistic, chi-square C, which on the next page is just referred to as chi-square. I don't know chi, I don't know phi squared per se. I mean, it's really not clear at all what they did. So a lot of this work basically was statistically not particularly sophisticated. And I think to some extent that is also responsible for the fact that there was less of an adoption of this kind of learner corpus research work in work on second language acquisition than was desired. And so here in this code, I basically show that it's not possible from these data to represent the numbers they cite in this paper. But now, how would we do this better? Okay, so as a first step. So a first step might be to actually, let me do this here with a regression model, because that's how MuPDAR actually originally was developed. And so a traditional LCR approach might consist of something like this, which is already a little bit better than before, and actually also points us in the direction of how we can do things better in general. And so that might be something like this, namely we fit a model where we say, okay, complementizer, yes or no, is it realized or not, as a function of L1, because that's what traditional LCR often did. And as you can see, I'm restricting the output here only to the coefficients. And so we can see, we can see a result for English, and then we can see results for German and for Spanish, and they are hugely significant. So the non-native speakers behave very differently from the native speakers. The model is significant. Everyone differs from everyone. So fine. But now the first thing one might ask oneself is, well, but so how good is this model? I mean, how much does it actually explain or predict? Okay, and one can do that in a variety of ways. Many of those are probably known to you guys. So one would be an R-squared value or a classification accuracy or a C-score. You know, many of these are routinely reported these days in the relevant literature. And if one does that, does any of these things here, the results are just super awful. Okay, so the R-squared value for this model, although everything is through the roof significant, you know, is a joke. I mean, it's not even 5%. It doesn't explain anything. The classification accuracy is at baseline. It doesn't do anything. There's no discriminatory power of this. And the C-score is terrible. You know, it's supposed to be, I mean, it's between 0.5 and 1. It's supposed to be 0.8 and above. And it's, I mean, it's 0.6 if you round generously. So it's awful. Now, why is that? Well, there's two reasons here. And they basically threaten the kind of validity of this kind of approach in two different ways. So one is, well, by now, you know, several of these might be straightforward, but still. So one is concerned with this repeated measurements nature of the data. Okay, so the way in which traditional LCR has proceeded literally for decades is by ignoring the fact that often one or more learners produce two or more examples that make it into the analysis. Okay, and that's especially in learner corpus research, maybe more than even in some other applications where it's maybe only statistically a problem. In learner corpus research, it even comes with a conceptual interpretation problem. So imagine this, you know, a learner always realizes the word that, even if the context, you know, when you look at it as a native or near native speaker or something like that, or you have a native speaker look at it, you know, the context screams like you got to omit it here. Okay, like everything in the context very, very clearly votes in air quotes, you know, to not realize that. But the learner puts it there anyway. So what does that mean? Well, actually, we don't know. Because, I mean, there's at least two things it could mean. One is our ideas of what triggers that realization or omission are just totally wrong. You know, we're looking at the context and we misinterpret the signals that the context contains, like, you know, don't realize it, blah, blah, blah. We're just wrong in that assessment, right? And this learner is just showing us that, you know, because the learner put that in there, that conflicts with our misguided expectations. And so, you know, this is great. We've learned something, namely that our account of that realization omission was wrong. The other possibility is this, you know, and again, especially relevant in learner context, namely that our ideas of that realization omission are actually spot on. It's just that the learner doesn't know how to use it properly at all. In fact, maybe the learner hasn't even learned yet that this is an option, right? That doesn't have to be there, but that it can be omitted. Okay, so in other words, and again, important here, you know, if we neglect the fact that the learner doesn't know one can omit that, then every data point that the learner contributes, where he or she realizes that, you know, would look to us as a piece of evidence against our ideas of what triggers that realization or omission, right? Because we think, wow, look here, here's all these cases, you know, where there shouldn't be a that, but look at these learners, you know, they always put it in there. So then every one of these cases looks like undermining what we thought we knew about this phenomenon, right? And so obviously with learner corpora, you know, this could easily be hundreds of pieces of evidence in big air quotes, right? Now, the other possibility is that the learner might not know that. No pun intended. The learner might not know that one can omit that. Now, if we considered that fact, you know, obviously everything would change quite a bit, because then we could say, okay, so not everything this learner does, you know, is evidenced against our ideas. On the contrary, what we need to do is we need to adjust our analysis for this set of weird cases, this set of unexpected cases, by realizing, okay, that learner is sort of different from maybe the others, in the sense that, well, he or she hasn't realized yet that there's actually an option, a decision to be made. And so, you know, we shouldn't consider all the cases by that learner as piecewise, you know, disconfirmation or falsification of our ideas. And here's an empirical way to show what that might look like. Okay, so here I'm loading two hypothetical data sets that are very, very similar, and they are actually designed in such a way that they're very similar to our original, to the actual data set. Okay, so one data set here, X hypothetical 1, okay, and then X hypothetical 2, which are loaded or created somewhere, you know, it doesn't really matter. The key point for you to notice is that, you know, they are really similar, right? So in both cases, we have the three L1s and we have the two levels of complementizer, and you can see, you know, the distribution is exactly the same, right? This table is exactly like that table. The correlation between the row and column variables in both cases are the same, right? So if those were two studies, you know, like two different studies that looked at the same data, you know, but one did this, you know, in Germany with this data set, and one did this in Australia with that data set, you know, then according to the traditional LCR approach, they would come to the same result, right? Because the frequency table is the same, the correlation table is the correlation coefficient is the same, and so obviously, you know, the p-value and whatnot would be the same, right? But I'm pretty sure you can see where this is headed. You know, the data sets are not the same at all. They could, in fact, hardly be any more different. Okay, because hypothetical data set 1 looks like this, and I'm only showing 2 rows of this table here, right? Let me show you. So this, yeah, 1 second. Right. Let me move this over here, maybe to the other screen. It doesn't like that. Okay, so this here is actually this. Okay, and you can see that here, every German learner either never realizes the complementizer or always does. Okay, no exception. Same thing down here, you know, we're now getting to the bottom of the screen, can't see it properly, but I mean, it's the same logic, and I'll scroll down in a second, obviously, right? So the Spanish learners, either they never realize the complementizer, or as you will see in a second, you know, they always do, right? That's what hypothetical data set 1 is. Okay, right, so here's the other one. But now hypothetical data set 2, which again, remember, it has the same overall totals, looks like this. Okay, so now every German learner uses these 58 items that they're using exclusively with complementizer absent here. Now they're using them, you know, and actually I made it such that the distribution within each row is basically compatible with the overall column totals, right? And same thing for the Spanish speakers. So I mean, within that L1, right? So the Germans in general, they use absent a little bit more than present, and so we get something like this. Spanish learners a little bit the other way around, so this number is always a little bit higher like that. But again, both of these results, I mean, this table and this table reduce in a traditional LCR approach to this. Okay, and so obviously, I mean, I hope, obviously, you know, reporting a p-value on this without checking, you know, which of these situations is it, doesn't make a whole lot of sense. You know, I'm sorry to say. Right, so every speaker is compatible with that overall distribution, but, you know, you would not want to use a statistical approach that treats these two things the same. Because here, you know, one might question whether any of the learners actually know they have a choice. And so, you know, do these 48 instances actually mean something other than the learner doesn't know? Whereas here it's clear that every learner knows there is a choice, and if they don't realize the complementizer, then that means something. It might still mean that they pick up on the wrong cues in the context, but they pick up on something. Okay, so that's reason one why this traditional approach is not great, and the first thing we want in a Mapdog approach to do better. The second one is concerned with the kinds of predictors involved. Okay, and so here in a nutshell, and for people who know mixed effects modeling well enough, that sentence would say it all, and I could stop there, but of course I'll explain it. The other problem is that the traditional LCR analysis doesn't consider any level 1 predictors. And that's the reason, or one big reason, why this R² value and the C-score and all that, why all these results are so terrible as they were. Okay, so what does that mean, level 1 predictors? So to use the regression modeling language here, typically we have a response variable, right, which here is the individual speaker choice for a certain context, right? Is there that or not, right? And that's level 1, the level of the individual speaker choice or decision or the linguistic event, basically, in whose distribution and characteristics we're interested in. But then in a normal regression context, we also have predictors at that level, right? I mean, you all know that, if you do corpus stuff, a lot of the time we spend on doing a concordance of something and then putting that something into a spreadsheet, and then we annotate every case, so every speaker choice of interest, that is there, that is not there, that is there, blah, blah, blah. We annotate it for a variety of contextual features, because then we want to run some sort of predictive modeling thing on it to see whether we can, with a reasonable degree of accuracy, predict what's happening, right? And so in this case, that might be predictors such as type. Is the complementation where a speaker chose to realize that or not? Is it object or subject complementation, right? Or this one here, I should have picked better, easier to pronounce variables. So the length of any material before the matrix clause. So in the above example, it was like, seriously, I really hope that, blah, blah, blah. So that would be the word seriously, right? The material before the matrix clause even begins, right? Or the matrix clause subject, right? In the example before, that would be I, the word I, right? Seriously, I really hope, blah, blah, blah. So then it's the word I, right? And so for every linguistic choice of interest, we note down these values of these predictors, and those are level 1 predictors because they're at the same level of resolution or taxonomic organization, if you will, as the phenomenon. But here's the thing: much work in traditional LCR glosses over all of that, right? In our simulation of the traditional LCR work before, we didn't look at the contexts. We just cross-tabulated, is the complementizer there, yes or no, with the L1. And so there's no L1 predictors. And indeed, in a lot of cases, there's not even predictors from the next higher level, such as level 2 speaker, which of course typically would be a random effect. But as I say, a hypothetical, but unfortunately pretty damn representative example of a traditional LCR study considers only one variable at an even higher level of abstraction, namely level 3. Okay, and so here you can see an example of what this looks like, right? So the complementizer here, that's, this column, obviously, that's level 1, right? The level of the individual choice. And then these two are as well, because those are variables, where for every thing in your concordance, you annotate, okay, what happened there, right? But then level 2 would be speaker, because, for instance, you can see kind of, these 3 instances of our level 1 variable are nested into the same speaker, which is just complex statistics speak for, well, they have been produced by the same speaker, right? And then these 4 instances of something, of the, that or not, those are from the second speaker, B. Okay, so these things are nested into the speaker, which makes that a level 2. And then what traditional LCR approaches looks at is actually only the next higher level, namely L1, right? Where this is one speaker from this L1, but later there will be other speakers from that L1, right? Speaker F, right? So we have a hierarchical structure there, which is basically, I really suck at drawing, but hopefully you can get it. We have data points, which are multiple points from the concordance, but several of them might all be speaker A, and speaker A is, a native speaker with L1 being English, but, speaker F and speaker G, let's say, and speaker H, those are, different data points, but they might all be the same L1, namely English, right? And so that's how this is level 3, this is level 2, this is level 1, right? And I mean, somewhat polemically, but who in their right mind would ask a question of, like, does the choice of whether or not to realize a complementizer depend only on what your L1 is? I mean, no one, right? I mean, I hope we all agree that, of course, there will always be a ton of linguistic contextual predictors, which will typically be at level 1, that have an impact there. And second, so we would need those predictors. And second, we would need level 2 predictors to account for the fact that different speakers behave differently, right? That's what we had before in the repeated measurements part, right? And so that's why the R-squared value and the C-score are so crappy, right? Because you're not looking at anything having to do with the context. You're not even looking at anything having to do with the speaker. You're just, looking at L1, glossing over everything else. And that's, of course, not going to ever result in a decent classification accuracy. And that's really ironic because there was early work in LCR, which very specifically and very greatly actually said exactly what one should be doing, right? So traditional LCR promoted, and here's this insightful quote, comparing or contrasting what native speakers and non-native speakers of a language do in a comparable situation. Okay, so in the situation that a learner is in, what would the native speaker do, or the other way around? Here the native speaker did X, would the learner get that and do the same? So, that was already set 1990, but LCR promoted that, but they didn't do that because it didn't include a lot of times any level 1 predictors that describe the context, or any level 2 predictors that describe the level of individual variation, right? And then LCR promoted keeping the group perspective while at the same time taking individual variability into account. Yeah, but individual variability was not taken into account because, we just cross-tabulated L1 with complementizer, and we didn't do, or traditional LCR doesn't do this, namely cross-tabulating every speaker, right? So they said to do all the right things, but then the analysis that were actually published didn't do that, right? And so where is the account of individual variability supposed to come from if you don't have level 2 variables in your chi-square test or log likelihood or whatever, right? And so as I say here, this is such an important point. I want to make it one more time with another hypothetical version here of the data set, just for the skeptics. And actually, because yesterday I reviewed a paper that got that wrong. So here's an example. These are made up data, right? But made up data on the same phenomenon. So I've simplified the L1 variable to just English versus other, right? Basically native speakers versus non-native. The response variable is the same as before, okay? And then I did something that one normally wouldn't do. I'm just doing that here for ease of didactic presentation. We're looking at the length of the material between the subject and the verb of the matrix clause. Let's say in syllables, again, made up data, it doesn't really matter. And so we might see, okay, we have 120 cases where that material is between 1 and 3, probably more likely characters. 150 cases, 4 to 6 characters, and so on. Okay. So what did traditional LCR do? Well, this, right? Native versus non-native, absent versus present. We get this distribution, super significant, because the native speakers have basically a 1-to-1 ratio of absent to present, whereas the non-native speakers have a 1:2 ratio, kind of. Okay. So that's obviously significant if you have, what, like 900 data points residual. So we can see that this is preferred, blah, blah, blah. And then, you know, worst case scenario, they write that up, right? But it's nonsense, because this significant overuse result is completely due to the other variable that is here ignored. Okay, namely the variable that counts like how many characters are in between here. Look at how this variable is distributed. Okay, so here we have 1, 3, 4 to 6, 7 to 9, and so on. Okay, and it's distributed in a way that kind of makes sense in a lot of learner applications, namely that, you know, the short material that maybe poses less planning and processing problems and whatever, that's overrepresented among the learners compared to the native speakers. And then the longer that material gets, the more the native speakers actually do it, right? Because let's say, you know, they have the processing resources available to squeeze something between the subject and the verb of the matrix clause. No problem, right? And that, the distribution of this predictor with L1, that is where this significant result comes from completely. Because look what happens if we cross-tabulate everything. If we cross-tabulate this length thing, L1 and complementizer, you know, and obviously made up, you know, but still, within every length group, the distribution of absent versus present, English speakers versus, native speakers versus learners is the same, right? When this thing is 1 to 3 characters long, we have 5 to 95% from both the native speakers and the learners. When this thing is 7 to 9 characters long, we have a 20-80 distribution for both native speakers and non-native speakers. And when it's super long, you know, we have the same 80-20 distribution in the native speakers and the non-native speakers. Okay, so with regard to the complementizer realization in these made-up data, you know, the native and non-native speakers behave exactly the same way, right? It's always the same here whenever you compare English to other. Okay, so the significant result of the level 3 predictor here, okay, that significant result is completely due to the level 1 predictor, okay, that traditional LCR just ignored. And that's why this kind of aggregation where you gloss over level 1, like the length here, or level 2, like the speaker, often returns complete nonsense, right? It's very easy to see something in the L1 versus, in the native versus non-native speaker data that is actually completely due to a predictor that traditional work just ignored. And the thing is that even a super simple regression that doesn't do anything other than make sure that this level 1 predictor here is included already sees that. Okay, so if we do the dumbest regression model one can do on this, you know, complementizer as a function of the length thing and L1 and the interaction, you know, even that already perfectly sees that anything having to do with L1 is completely insignificant, right? The coefficient for L1 here has a p-value of 1, and the interaction, those all have p-values of 1. So that model already sees it, right? As soon as a level 1 predictor is in there, it sees that our cherished level 3 predictor L1 actually doesn't do as soon as the length predictor is in there, here, as soon as the length predictor is in there, the model sees that nothing with L1 that LCR research has always been so keen on, you know, actually does anything. Okay, and so those are the 2 main reasons why the traditional approach really doesn't do all that much. Basically, you know, if we had the time, I think we should redo all those studies to see basically, okay, so which of those chi-square tests, you know, actually hold up to scrutiny once all the other things are controlled for. And my hunch is not many. All right. I don't know how the question answering thing is supposed to go here, but I mean, this would be a good point maybe to give people an opportunity to ask comprehension questions, just to make sure that, you know, everything's clear before we move on, or do we want to do it all at the end?
Well, we do have one question. That would be, would a mixed model with learner in the random effect structure account for level 2 and level 3 predictors, but not level 1? Well, it would depend on which factors are included in the fixed effect structure, right?
Yes. So so that's a good question, and actually a big part of the answer is in this reference here. So when you get this HTML file, then after the section that we just went through, there's this literature thing, and here this article in 2018 in the Journal of Second Language Studies discusses essentially that kind of question.
Mm-hmm.
And so if you so a level 2 effect such as speaker, would typically be part of the random effect structure. And so if the if you wanted to just see whether the whether a certain speaker has a completely different baseline of realization of the dependent variable, then you would put varying intercepts in there. If you wanted to see whether a speaker reacts very differently to some cue that is embodied in a level 1 predictor, you would need to have varying slopes in there, right? So for example, in a model like this, okay, so like this, complementizer as a function of these two things, if you now wanted to see whether speakers react differently to this length thing, then your random effect structure should be plus, and then intercepts plus, I'm going to abbreviate this, plus the length thing for every speaker. And then provided that you have enough data points, which of course in LCR often is an issue, but theoretically in an ideal world, if you had enough data points, then this intercept adjustment for the speaker would tell you, okay, how likely is the speaker to realize the complementizer in general? And this slope would tell you how sensitive is a certain speaker, to variation in the length of this intervening material, right? And so theoretically, it would be possible, or what can happen is that, let's say, if the speaker is, completely overuses the complementizer, maybe not even ever not use it at all, then that intercept adjustment might be super high, because that's the model's way of accommodating for the fact that it has to always return a very high predicted probability for the complementizer being there.
Mm.
Yeah.
Yep. Otherwise, I haven't received any questions so far.
Okay.
But if people have questions, feel free to post them in the chat, and I'll note them down and either read them out or I'll ask you to ask them.
All right. Sounds great. Okay, so then that's actually good, because then I've been monitoring the chat window too, but there was nothing. So let me close that back. All right. Okay, so then MuPDARF. So what does it do? And so now we know why, we need something like that. Maybe not exactly MuPDARF, obviously there's other ways to do things, but why we need something like this. So in order to discuss this, we're now going to look at the data set as a whole. So let me introduce you to the other predictors of interest. Okay, so again, the sentence in question that exemplifies all of this is, seriously, I really hope very much that, or not that, the Vorlons will help us against the shadows. And so we have a bunch of numeric predictors. Predictors in the regression model. The first 6 are essentially, in this simulated study here, are essentially control variables, and they refer to the lengths of various positions in the sentence. Okay, so the first one we already saw, the length of any material before the main clause. So that's seriously here, the length of the matrix clause subject. That's just the word I. The length of material between subject and verb of the main clause, which here is really, okay, material between the verb of the matrix clause and the complement clause, which is here, very and then much. So very much, 9 characters with the space. The length of the complement clause subject, the Vorlons, and then the length of the rest of the complement clause. So all that stuff. Okay, so those are the variables that we will consider as controls here. But of course, critically, those are all level 1 predictors, right? They differ from case to case. I mean, they will be different in every, not every, obviously there will be some repetitions, but they will be different from every application of a learner, using that or not. Then we have two sources of random effects variation. And so one would be the file, which is just the speaker in this context. Okay. And then the other one would be the verb of the main clause, which here, of course, would be hope. Okay. And then in this simulated application here, we have two predictors of interest. Okay. So we're saying, these we're actually not interested in. We're just putting in there to control for whatever they might do. And of course, all of those amount to a certain degree of, processing complexity, right? How much material is there, that the speaker, and especially the learner, has to stay on top of as they assemble and incrementally produce the sentence. But the two predictors of interest then are these two. So first, DPWC, so that stands for delta P word to construction. So that's the degree to which the matrix clause verb, hope, prefers that omission. Okay, we know from, well, by now, what seems like 50,000 years of constructional work that verbs have, words have preferences for grammatical constructions. And so here the idea is, is it maybe the case that certain items, is there an overall correlation between what verb is often used with that or not that, and how it is being used here by the learners. And then second, we're going to look at surprisal, namely the degree to which the last word of the matrix clause, which here is much, is predictive of the first word after the that slot, meaning the. Okay, and so those are operationalized basically on the basis of conditional probabilities from the British National Corpus. So negative binary log of, how much, what's the probability of the given that you've just seen much. Okay, so that's what we're going to do. So 6 controls, 2 level 2 random effects variation things, and then 2 main predictors of interest. All right. Now, as you can see, about 6,000 observations here. And now we're going to use it to exemplify MuPDARF. So what does this approach consist of? Is that a chat question for now? I think that might be a question for later, if that's okay, right? Because it's not relevant for understanding the next step. Peter, is it okay if I respond to that at the end of the talk? Okay, perfect, thanks. If I don't come back to it, I'll leave the chat window open, but then just remind me, insist.
I've noted it as well, so it's cool.
Yeah, and so yeah, match lemma and DPWC will be collinear, but the fixed effect, of course, but only in one direction. If you know the match lemma, you will know the DPWC value, but theoretically it need not be the same way the other way around. So the varying, so something like varying intercepts theoretically of, if we did a regression model and not a random forest, the intercepts would basically capture whatever is left after the association measure has been accounted for. So that's actually not uncommon. Okay, so what does Mapdog do? So it's basically a missing data imputation kind of approach. Okay, and so so that's a method that is used in some disciplines. I haven't actually seen it much in linguistics, but it's a method used a lot in other areas, where like for instance in survey methods or something like that, where maybe subjects do not provide all answers to a questionnaire survey, and so many methods would then not work because they can't work with missing data, right? In a regression approach, if you have one missing data point for one case, you can't enter the whole case into the regression model. And so you can either throw the case out, or you can try to impute, okay, what's the value that's most likely, or that would have been there, had the speaker provided the response, right? And I mean, I know it's difficult in these, or it's dangerous in these political times to give a political example, but it just fits so well. So if we, I mean, just imagine a case, presidential election polling in the US in 2016, or even after the election, right? So everyone trying to understand the result, given that it was not the result that was overwhelmingly predicted. And so you might look at your polling results, and maybe you have a questionnaire survey where someone didn't actually say who they voted for in the election. Okay, but they provided everything else. And so you might now say, okay, can I impute what that person might have done? And then, if the person's other responses in the questionnaire were that, he was a 55-year-old white male with only a high school degree, living in rural Kentucky, having a manual labor job, being super religious and whatever, well, guess who he voted for? At least with a high probability, right? That's basically imputation. And so what are the missing data that we do impute? Well, so in learner corpus research, it's one of these two things, namely, and this should sound familiar because we looked at this Perry Woodley quote, what we usually don't have in learner corpus data is what a native speaker would do in the situation that a learner was in, right? I mean, learner corpus data means, we have the production of the learner in the form of a corpus file. What we do not have is, typically, at least unless we create that manually later, what we typically don't have is a second file that says, for every non-native speaker choice, a native speaker saying, yeah, I would have said that. Yeah, I would have said that. No, I wouldn't have said that. And so on. That's basically what is imputed here, right? Which also means that this is kind of like an assessment of the acceptability or naturalness of what what a non-native speaker choice looks like. Right, so essentially in a learner corpus context, we're imputing some sort of rater, actually, like a native speaker rater that goes over the data and says, yeah, I agree with that choice, I agree with that choice, I don't agree with that one, blah, 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 something like that. Okay, and then I provide the same here for the other main area in which MuPDAR has been applied, but I'm not going to discuss this here. You can read up on that later. And so then the approach looks basically like this. So here's a 4-step procedure, and I'm kind of already to showcase how this would look like in R using a regression modeling language. So you first apply a regression or some other kind of classifier or predictive modeling technique to only the reference speakers. Okay, and so the reference speakers in the learner corpus context are the native speakers. Okay, so it would be something like this. Regression 1 is, let's say, a G-Elmer or something, namely whatever linguistic choice as a function of hopefully a ton of predictors, but only for the reference speakers. Okay, and then if that thing works well enough, then we use it to impute for every target speaker choice. So in the learner context, that's the learner, what the reference speaker would have done or said in the same situation. Right, and so in R, this would be something like, imputed choice is, well, predict on the basis of the native speaker data what the target speakers would have done, right? And that's what the Perry Woodley quote was about, namely what the speakers would do in a comparable situation, right? And so comparable situation is now defined by all the annotation that is in this data frame, containing the hopefully many level 1 predictors, but also level 2, level 3, whatever else. And then for every learner choice, we have 2 data points, essentially. We have what the learner actually did, but also what the native speaker was predicted to do for that. And so we now compare them. And one way to do this would be the simplest one. I'll present a better one later. Namely, we just check, are they the same? Okay, is the target speaker choice the same as the imputed choice based on what the native speakers did? Right, so for instance, a native speaker might have realized that. A non-native speaker might have realized that, and a native speaker is predicted to have realized it as well. So then the native speaker and the learner choice are the same. Or a learner might have not realized that, but a native speaker would have. Then the approach says, okay, that choice is not native or reference speaker like. Okay, and then finally, and that's in a sense for interpretation, the most important step, then we have this reference speaker like variable, which could just be a binary yes, no thing. Okay, that is subjected to another round of modeling, namely, again, the same predictors for the target speakers, because now we're trying to figure out in that second step, okay, so what is it that makes the non-native speakers make choices that are not what the native speakers would have done? Okay, and then I have this little plot here. Let me see what I can quickly show you that in a better resolution. Yeah, like this. So that's the thing you will see on the screen in the HTML file. It's basically the same thing, but it gives you a little bit more detail, right? So it goes from top to bottom. So it's like the time course of a MuPDAR analysis, from step 1 to step 4, and then it has the 4 steps here, and then wherever there's multiple steps involved or multiple options, you can see them here. So generating a model of the reference speakers is the first step, and this could be any kind of these things. Evaluating the predictive model quality could be any of these or all of these, of course, and so on. And so once we're done, you'll see when you revisit this plot, you'll see at every step, what we've done all along the way. Okay, so to get ready for this here, we split up the data into 2 parts, one for the native speakers, one for the non-native speakers. Okay, so I take the data, split them up by whether the L1 is English, because that would be the native speakers. And if it is English, true, then I call that NS for native speakers, obviously. And so we have these examples here. And you can see that now L1 only contains English, like no German and Spanish anymore. And then the non-native speaker part is when L1 is English is false. Okay, so that leaves us with these 2,400, 500, whatever cases of the learner data, right? And so now there's no English here, right? So we'll train basically the classifier on the reference speaker data and then apply it to the target speaker data down here in a separate data frame. Okay, as those of you who had the privilege of being tortured with a bootcamp in myself, we'll need to compute baselines. So we will compute in order to see whether our first classifier does a decent job. One thing to do, among others, is to compute like, okay, so how well would the dumbest possible classifier already do? And so we compute a baseline classification accuracy that we need to beat, which here is about 68%. Okay, so that's the distribution of complementizer absent to present. So if we don't get at least, this ratio right, then, you can't do this approach, then it doesn't work. Then there's not enough structure in the data to be used for making these predictions. Okay. So this first step, let me actually bring that graph back. Okay, so right now we are here, generating a model of reference speakers. As you can see, there's a variety of options here. Probably by now, still linear mixed effects modeling of some type is the default, but we're going to use a tree-based approach here. Well, actually, we're going to look at all of them, but for the most part, I will rely on tree-based approaches and then some others along the line. So, and also note here, I'm not doing any data exploration or something like this here, because we don't have all year, and this is not a predictive modeling bootcamp, to talk on MuPDAR. So obviously, if you did a regression analysis kind of here, then you would have to do a ton of exploration, preparation, transformations, everything to make sure that the model, that the data are actually of a type that allows for regression modeling. Again, in the interest of discussing MapDog here, I'm going to skip that, but something to keep in mind. So the model of the reference speakers could be generated, for instance, like this. Okay, so complementizer as a function of the two predictors of interest. Okay, obviously those have to be in there. Then a bunch of controls, all of which have to do with the matrix clause. Two controls that have to do with the complement clause, right? And then some random effect structure, right? Crucially, done only on the native speakers. Okay, and then we get something like this. Okay, and at least looks like there's a ton of significant stuff here, although surprisal doesn't seem to be significant, but still a lot of significant stuff going on. Please. Now, how would the random forest approach look like? Actually, do I have to explain what random forests are?
I think it should be fine.
Should be fine. Okay, just checking. All right. Okay, so a random forest then could look like this. So I'm using right now here, I'm using this package and this function, but the other packages that are often used in linguistics like party or random forest or whatever obviously work in very, very similar ways. So same thing, the response as a function of the two predictors of interest, the 6 controls, and what would be random effects in a mixed effects model. And again, just on the English bit. And we get this. And then very briefly, I don't want to discuss this much, but it's too interesting, I think, in general, to leave out completely. So there's a third option, like I say here, the case-wise similarity approach. So there, the idea is that you don't do something that involves regression modeling, or you don't do a tree-based approach or something like this. But instead, what you do is you try to predict, or you make a prediction for each case, for each complementizer realization, yes or no. And the prediction you make is what speakers did in cases that are very, very similar to the case in question. Okay, so if there was no material before the main clause, but a lot after the verb of the main clause or something like this, then basically what this approach involves is looking at all sentences, at all matches, and find, okay, what cases are like that? And then let me predict that the speaker here would do, what all the other speakers do in the same situation as measured by similarity. I mean, it's simplifying a little bit here, but you see the code. The advantage of this is that this is something that doesn't involve. I mean, obviously, it doesn't have a lot of distributional assumptions because it doesn't involve matrix algebra and whatever kinds of mathematical subtleties. It just involves similarity comparisons. And for some people, at least, I wouldn't necessarily include myself on those, but for some people, at least, who are interested in cognitive reality of modeling approaches, something like this might be interesting from the perspective of, well, this is kind of an operationalization that could be couched in terms of similarity of something within a multi-dimensional exemplar space, something like this. So this is kind of like memory-based learning or something like that. Anyway, just the third approach, that can also be used. And sometimes, it works better than others, sometimes it doesn't. And that's what we need to look at now. So now we have 3 different predictive models, a regression, a forest, and this case-wise similarity approach. And so now we need to see, okay, which one does best, right? Because then that's the one. So if we want to make predictions for the learners based on the best model for the native speakers, right? The predictive modeling approach that finds most or nearly all of the structure in the native speaker data, that's going to be the one that we want to use as our, imputation of a rater of a native speaker who reads all the learner data and then decides, would I say this or not? And so again, obviously, I'm not going to go over the code here a lot. Some of you might see it in the bootcamp later this month. But so for the regression model, we're generating all the predictions, and then we can compute classification accuracy. And then we can compute precision and recall both for, is the complementizer there or is it not? Okay, and then depending on what you want to emphasize, you can work with any one of these. Good thing to see already is that the baseline was 68%. Here we're at 84%, so the classification accuracy is substantially higher than the baseline. So that seems like, okay, there is something to work with. I'm going to use the opportunity to promote yet another measure, which is called log loss. I think I provide a link somewhere later here. If not, I can try and remember and give you that at the end of it. So log loss is a value from the machine learning literature. I mean, it's an evaluation metric from the machine learning literature to give you basically, well, it can give you different things, but one way of looking at it would be a single value for a classification task. And so you can use it for exactly the kind of situation that we have here, namely you have different algorithms run on the same data, right? So here we minimally have a regression model and a random forest. Let me leave aside the case-wise similarity data approach for a moment. So we have two approaches on the same data. And if you want to see which one does better, then apart from these things, accuracy, precision, recall, you can also take a log loss value to see, the higher that value is, the worse the algorithm does. So you would want to use the predictive modeling approach that returns the smallest log loss value. And I mean, I know this is not the topic of the session here, but I really, really would encourage you all to look at this value because it's insanely useful. And actually, it is connected in a variety of ways to many regression statistics that many of you might have heard of, but actually never completely fully understood. Okay, so if you've always wondered, okay, so what the hell is deviance in a modeling context? What the hell is the log likelihood value and AIC and deviance? How are they all related? Well, in one way of looking at it, they're all related by log loss. So it's a theoretically extremely insightful thing to look at. It'll make fall a lot of maybe disconnected things into place. At least it did for me. All right, so we have for the regression model, we have some statistics like this, and the log loss value, same for the random forest. Okay, and we can see in this case that the random forest does a little bit worse. Okay, the accuracy here is 83.8, and here it's 81.6%. The log loss value is also a little bit higher. I will comment on this in a second. And then for the case-wise similarity approach, we can see here that it's actually even a little bit worse than the random forest. Okay, you can't compute log loss for this one for reasons that don't matter right now. Now, the regression model and the forest don't differ much, but they're both better than the similarity approach. And then the other thing one must not forget is that the regression model here, the accuracy that I'm computing is classification accuracy, but the random forest is returning prediction accuracy, right? Because the random forest returns predictions for cases that were not used in its training for all those trees. So, it's not surprising. I mean, a lot of times random forests do better than regression models, but sometimes, if there's a small difference, part of it just comes down to the fact that the random forest actually reports a statistic that is more demanding. And so in this case, for didactic reasons, because of what I want to talk about later, we'll go with the forest, but those are kinds of considerations you have to have in mind when you make your decision what to go with. So we apply the model to the target speakers. Okay, so this is step 2 now. Okay, so we did the first part. We only looked at classification and prediction accuracy. I didn't do cross-validation for lack of time. So now we apply the model to the target speakers. And you know what, in the interest of time, I'm just gonna show you the random forest. Let me just note the log loss from the regression is 0.71. Now we make the predictions based on the random forest. And the log loss is a little bit lower. So the random forest actually is better at predicting or making predictions in the learner case than the regression model. So that's a nice thing to see. And then the case-wise similarity approach, the way this one works, I can talk about this more in the Q&A. So this one basically says, okay, here's a case of the learner data. What did the native speakers do in cases that are like that? Okay, but with no equation, no weighting, no nothing in a sense, just by looking at, okay, so what did they do in similar occasions like that? Making predictions like this. And again, in this case, it does a little bit worse. In other cases, this approach actually did best, so it can vary. So the random forest does best, and we're going to go with that. Okay, so now we've done this bit. Okay, so next step, determining reference likeness of target speakers. And as you can see, there's 3 ways to do this. Most studies did the first one. The second one was only recently introduced, and then the third one was introduced a while ago, but there's different ways to do it. So the simplest way to do it is, this binary construct thing that I mentioned earlier. Let me start with this one here. Actually, skip this. So we just check whether the learner made the same choice as the native speaker is predicted to have made in this case. Okay, yes, no, that's it. So if the learner is realized that, but the native speaker was predicted not to, then it's a dangerous word these days, wrong, then it's not native speaker like. Now, as a graded construct, that one is better than this binary thing because it's more precise, right? Imagine a scenario where where the learner produced that, okay, but the native speaker was predicted to not use that with a predicted probability of 52%. Okay. Now imagine another case, the learner didn't produce that, but the native speaker was predicted to produce that with a predicted probability of 98%. Okay, so in that case, the binary approach would both say, the learner did it wrong. He didn't produce what the native speaker was predicted to produce. But what the binary approach doesn't see is that, in the case where in one of those 2 cases, the learner is basically off by 2%, the native speaker was only predicted to make the other choice by 2% more than the 50% cutoff point. Whereas the other example was a case where the native speaker was predicted to say, no way in hell can you do this there. It's just totally wrong, right? And the graded way of doing this would accommodate that kind of difference. So it's a more fine-grained solution. It is, and also moving in the direction of acknowledging the fact that a lot of cases, in some alternations, most of them, you can actually do both. I mean, they're both grammatically acceptable. They just come with different degrees of deviation from the predicted native speaker norm. And so one can do this either with a signed deviation score that was used in some previous work, but that I'm not going to use here. Here in this talk, I'm going to use log loss again, and it has some advantages that I'm not going to bore you with now. If you want to talk about those later, let me know and I can discuss this. And then in the case of the binary alternation, at least there is a third option, a paper that was introduced in the paper with Sandra Vizor just last year, I think, where we allow for an option of, either choice would be fine. So if the native speaker is predicted to say X, but with a predicted probability that is actually relatively close to, well, I could also say the other thing, then the model can return something like, what, here both would be fine, so we don't want to overzealously count what the learner did as wrong. Again, read up on this, you will see it discussed here in great detail and with the code and everything, so you can run this later. But, those are essentially the 3 options. And I'm actually, in the interest of time, I'm going to skip those, like 252 and 253. We're just going to talk about the log loss approach here, but browse this later at your convenience to see how those work. And so I'm computing the log loss here. So how far off are the learner choices? You can see most of them are, so log loss is here on the x-axis, and the smaller the value, the better the choice. And you can see, most of them are pretty good, but then there's some choices that are really, really off. And hopefully we'll be able to model this properly later. And so then the last step, right? So we did determining reference likeness of the target speakers as a graded construct using log loss. And so now the last step is modeling of this. Excuse me. Where we, oh damn it, there's a typo in there. Okay, whatever. So where we will generate a model of the target speakers and maybe do model diagnostics and definitely interpretation. So that's what we turn to now. And again, we're going to use this with a random forest. So now the log loss, so the degree to which every learner choice is maybe a little bit off of the native speaker choice, that is modeled as a function of the two main predictors of interest. Okay, but now also the L1 of the learner, because now we have two L1 learner groups, right? We have German and Spanish learners. And so we will want to see, is there a difference between them? The actual choice that they made, right? Because maybe we find out that mistakes are mostly made when the complementizer is not realized, or whether it is. And then the 6 controls from before and the 2 random effects from before. Okay, and with that predictor structure, may I draw your attention to this triumphant number? Pretty damn great. So obviously, there is a lot of structure there that one can talk about. So let's try and, understand how this works. We're not going to do much model evaluation, diagnostics, and validation here, simply because in a random forest, much of that is much less necessary than in a regression modeling context. So we're just going to do a little plot of how well the forest is doing. This is basically an observed versus expected kind of plot. Okay, so we have the observed log loss values here. That's how far off the learners were. And we have the predicted values from the random forest here, and then the main diagonal. And so obviously we would like to see most data points clustered pretty much around that, and we do. Right, and then the grid lines here, those are the deciles. Okay, so we can see that more than 70% of the data are actually just in this small range, right, going until here. And this is where the values are green. So this is where actually the learner choices were correct. But so with some exceptions, on the whole, there's a pretty high degree of correspondence between those two. And we can, of course, compute that with an R² value or something like this. And so 0.93, that's pretty great, explained variance. All right, now the other main part after all this time that I want to focus on in this, namely, how do we interpret this? Okay, so we have a random forest, and well, some of you know me, so I'm blunt. Much of the work that is done with random forests is, let's call it suboptimal, shall we? People just don't use them right. And I know how arrogant it sounds, but I hope that at the end of this talk, and maybe at the end of the Q&A, you will agree that that is the case. So what does one need to do if you do a random forest analysis? Okay, so you need 2 things. One of them is pretty much always done. The other, not so much. But even the one that's done is often done wrong. So what do we need? We need variable importance scores. Okay, and what do? They assess how important a predictor is for making predictions. Right, so in our random forest, we tried to predict the log loss values right, on the basis of all these predictors. And so for every one of these predictors, we can get a variable importance score that says, you know, how much does this thing, and here's the most important word, somehow, how much does this thing somehow contribute to that? Okay, we'll see in a moment why I'm saying it that stupidly. Okay, and people provide that. And you know, my polemic explanation for why people provide that is, well, it's easy. You know, you type var imp and you got it, right? And so if we do that here, we get something like this. Okay, so complementizer. So those are sorted already. Complementizer is super important, and then interestingly, the correlation, the constructional value delta p, and then these other things, and actually L1 doesn't matter at all, and so on. So this is what people provide, but then already they actually don't mean what people think they mean. Okay, that's the bucket of cold water on the otherwise good news that this is usually provided. Now, the second thing that we need is partial dependence scores. And those are, in at least the work that I see, and maybe, you know, my input is not representative, but those are hardly ever provided. And that's actually really weird. So what do those do? They actually do what regression coefficients would do by virtue of their sign, for instance. They assess the directionality of the effect a predictor has on the predictions. Right? So, I mean, if you know that complementizer is important for log loss, you don't yet know in what direction. You know, does complementizer absent raise log loss, or does complementizer present raise log loss? So, I mean, again, not to drip with arrogance here, but it completely eludes me how people can say this is important, but then they don't provide a partial dependence score that says how. You know, that's the equivalent of what everybody bashes all day long when it comes to regression modeling. Maybe that's like saying, you know, this coefficient is significant, but now, you know, I'm not going to tell you in what direction, right? No one would dream of that, but with random forest, they do it all the time. Now, of course, people are aware that one should talk about this, but what do they often do then? A lot of times people use monofactorial statistics done post hoc on a random forest to say what a predictor does. Just the other day, I reviewed a paper where people used a random forest with like 15 predictors or so. And then they wanted to say, okay, now what does every variable do? And they did a chi-square test, a monofactorial chi-square test on every variable, and then discussed that as if that was even close to what a variable, I mean, to illustrate the ludicrousness of this, I mean, they used a monofactorial chi-square test to represent the effect that a predictor has in a random forest with 14 other predictors, right? I hope that kind of formulation makes clear how insane that thought actually is. Okay, but that happens a lot, plus some other things. Second, I hope to be able to convince you that this is also wrong. You must not use a single classification tree to summarize a random forest. It will not give you the right results. And I have a whole paper out there pretty much just on that. We'll see how far we get in discussing that. Okay, so what does a high variable importance score mean? Okay, and that's really important because I think more than 90% of the studies that I've seen get this wrong. Okay, and I'm just going to probably read this, you know, because this is how I say it in the new version of the textbook that just came out. You know, what we're getting from a variable importance score looks like a main effect. Okay, like complementizer on its own does a lot. That's what this seems to say, right? And that's how people talk about it in their papers. You know, wow, important predictor. You know, but what the variable score really means is complementizer is somehow important for making good predictions. Okay, and somehow is a technical term here. It means, you know, it might be a theoretically, you know, a strong main effect, right? Or it might be involved in one or more two-way interactions, or in one or more three-way interactions, or, you know, higher order interactions. Okay, And so let me make this obvious with regression formula syntax. If you have a model like this, y as a function of a, b, and c, then you might get a high variable importance score for c. Okay, and then everybody and their mother will write a huge discussion section on, what does c do? When the high variable importance score for c means that any of these things could be important. C on its own, and that is what everybody writes about. Okay, but a high variable importance score for C could exclusively be due to the fact that it participates in an interaction with A, or with B, or with both. Okay, and the thing is, you don't know. Okay, just from looking at this monofactorially, or just looking at this from the variable importance score, you will not know which of these it is. So, spare me those discussion sections that write 2 long paragraphs about, oh my God, how important is C on its own? If you haven't checked, well, is it actually C, or is it one of these other things? Right? And that's actually like in overview articles on random forests that are widely cited, that is clearly stated, but no one gives a damn, it seems. Right? So here's this, this is the best paper ever, on tree-based approaches. It's absolutely marvelous. The random forest permutation accuracy importance covers the impact of each predictor variable individually, and now the punchline, as well as in multivariate interactions with other predictor variables. Or the random forest variable importance may reveal higher importance scores for variables working in complex interactions. Okay, so like I say, studies that use random forests might have made a whole big monofactorial deal out of a predictor with a high score without ever realizing that the real reason was that that predictor was in an interaction. Okay, so that's what one needs to look at. So we need to look at, is there an interaction effect, and what are the partial dependence scores? So let's look at the first variable of interest for that. So surprisal. Okay, we wanted to see, does that have an impact? So here's a partial dependence score for surprisal, which looks like this. So on the x-axis, we have surprisal values. Okay, so the higher the value, the more surprising the beginning of the complement clause was. Okay, and on the y-axis, we have predicted log loss, i.e. do people get it, how much do people get it wrong, the learners, right? And then the size of the points is how many data points do we have in that range. Okay, and so you can see we don't have a ton of data points here, we don't have a ton here at the beginning, but where most of the data points are, there's a negative correlation, such that if it gets more surprising, the beginning of the complement clause, people get it right more. Okay, that may sound confusing, but it's the reason why that is so is if things become more surprising, then both learners and native speakers are more likely to put that in, probably as a way to signpost the beginning of the complement clause, help the comprehender or maybe themselves by buying time, by putting in the explicit marker of the syntactic structure. Okay, so that's the main effect of surprisal. Okay, but like I just said, we don't know whether surprisal, whatever effect that it has here, not that high, somewhere in the middle there, whether that is in fact the main effect or not. So far we've only said, okay, it's intermediate importance, apart from this one here. But so far we've fallen into the same trap as everybody else who doesn't realize, well, but maybe it's involved in an interaction. Okay, so let's see whether surprisal actually participates in the interaction, right? And I'm just going to do this here for lack of time, for 2 other variables. Namely, we're going to see whether surprisal interacts with A, the most important predictor, complementizer, right? Because that had the highest score here. So we're going to briefly look at that. And second, this is a learner corpus study. So why don't we check whether surprisal interacts with L1, right? Maybe surprisal works differently for the German learners as opposed to the Spanish learners or something like that. And so I'm computing those here. And of course, I'm not going to torture you with this, but you see, there's a ton of comments, blah, blah, blah. and then we visualize them, and this is where the interesting bit happens. Okay, it looks like this. So let's start on the left, actually. Right, so the blue is the Spanish learners, the green is the German learners, and you can see, I mean, they're totally on top of each other. Right, there's no difference in the blue curve and in the green curve. In fact, they're so much on top of each other, you don't even kind of see that those are two. Right, and also note that this shape here is exactly the main effect shape. Right, this thing looks exactly like this. So yeah, surprisal does not interact with L1. But now look at this. That's an interaction. Right? The effect of surprisal when the complementizer is absent is down here, and it's actually pretty pitifully small. You know, that line is pretty much flat most of the time. But when the complementizer is present, you know, then we have actually an exaggerated strong version of the main effect here. Okay, and again, that's why you need to look at this, right? A lot of people really, they just go with, oh my God, how important is this? And then they do a chi-squared. No, you need to look at what is this? Partial dependency scores. And then you need to make sure, well, and this is actually not tainted by an interaction effect or skewed by an interaction effect. Because, you know, here, I mean, I'm hoping you agree with me that you don't want to summarize, you know, a curve like the black one here, you know, when in fact this is what you find, right? So what is the nature of the interaction? You know, when complementizer is absent, surprisal doesn't have a strong effect. That's the part, you know, down here. For the range of values where most surprisal values are located, we say a very, very weak version. So there's a little bit of a down effect here, but of course it's ridiculously small, right? But when complementizer is present, you know, then we got this, right? So then it has a much stronger effect with, again, higher values of surprisal being associated with lower log loss. And so that one is also interesting because it fits very well with what we said before. Namely, you know, we said when it's more surprising, people put the complementizer in, it's present, and that reduces log loss, right? So if things are surprising and people put it in, their being wrong goes down, right? So because insertion of the that makes the syntactic transition maximally explicit, and that if the learners do that, you know, then that makes them more like the native speakers, meaning their log loss values go down. Okay. Now, second one, very briefly, the other predictor of interest, the correlational or the collostructural one, how much does the verb prefer a complementizer presence or absence? And it's similar, right? So we first do, I mean, we're conscientious, so we're doing partial dependency scores, but we restrict ourselves to a main effect first. And it looks like this. And so it's really, really not that strong at all, you know, and this is think. Okay, so one verb taking up the lion's share of a really strong correlation there. But there's a slight ascent. So if this value goes up, you know, then this goes up, so it goes up a little bit. But again, this is the main effect, right? We don't know whether the variable, I'm not going to scroll up, it takes long. We don't know whether the main effect of this thing, we don't know whether the variable importance score for this predictor is due to this main effect or also some interaction, right? So again, we're generating interactions of the collostructural thing with complementizer on the one hand and L1 on the other. And then we plot, and then again, it looks like this, right? So L1 makes no difference. I mean, how much more on top of each other could they be, right? So whatever the delta P value does, it's not because of, you know, differences between the two learner groups. But look at this, right? I mean, really, you want to write this in your discussion section because you're trusting, oh, well, you're hooked to the misleading interpretation that, you know, a variable importance score reflects a main effect. No, it doesn't. Here, whatever this thing does is, again, different depending on whether the complementizer is present or is absent, right? So the main effect interpretation of variable importance scores that pretty much everyone is using in their papers, it doesn't tell the whole story. You'd be completely missing this. Okay. And again, just to make that very clear, because people are always incredulous. I mean, this is not just me saying that, right? I mean, I gave you these Strobel et al. Quotes here, and if you read the, the biogenetics literature on, random forest and stuff like that, much of which is cited in the 3rd edition and in another paper that I'm referring to here at the end, we'll see that, I mean, there's no debate there. It's very clear that random forests differ in terms of what one paper called, the difference between detecting interaction and capturing interaction. It's just that knowledge somehow didn't make it into linguistics, and so the result is a bunch of papers, that misunderstand variable importance scores because they think they are main effects, because R makes it look like a main effect when it's outputted to the screen. It doesn't say, well, it could be all this. All right. So I'm doing, I maybe should come to an end here because the last thing you can easily look at yourself. It's not super complicated. So the one thing I would encourage people to use to also do at the end a lot of times is something like this, namely do some completely post hoc, post hoc exploration of the worst predictions. So where is the model of worst? Where did the learners go against the native speaker imputed choices most? And so here, this is kind of interesting. So it's totally arbitrary here, right? This is just a demo. I'm just looking at the 25 worst cases. Okay, and I was pleased to see that those were more Spanish than German learners. But interestingly, those are all cases where the complementizer was present. Okay, so they are wrong most, by inserting it, and they're all cases of think. Okay, and also they are all cases of the subject of the matrix clause being one character long, meaning those are all cases of I think, right? And so, and complementizer present. So I kind of summarize it down here, so the worst cases where the learners do worst are cases like this, where they have I think that, and then a very short subject of the complement clause. So I think that he, or I think that I, or I think that it. Those are cases where native speakers would leave out the, because I think is merely a discourse marker at this point. It's not like, okay, subject, verb, and now I have a complement clause, let me put the that in there. No, it's like, a single word, and then the that is not realized. And in these data, a lot of the times, and here at least mostly the Spanish learners, they didn't get that. And in Spanish, the complementizer insertion is obligatory, so there we probably have a transfer effect, right? So for those who are interested in applied contexts, which I am usually not that much, I have to admit, but for those who are, this would be, of course, a key insight, namely telling them, well, what if it's I think, just leave it out. Yes, it's not ungrammatical, but if you want to sound as idiomatic as possible, get rid of it. All right, so then down here, there's some references. So these are all applications of MuPDAR that I could come across with the links. Obviously, some of these things are under review or in progress. The log loss thing and the tertiary prediction, this is from these two papers. This is the paper that talks about how summarizing a forest with a tree is really, really a bad idea. I can talk about this more if you guys want to. And then two other general things that talk a lot about modeling. So let me open it up for questions at this point. But thanks for sticking with me for such a long time already.
All right, Stefan, that was fantastic. Thank you so much. I'm really grateful. Like, that was very, very interesting. I think super relevant for so many people who work with corpus data in learner corpus research. Yeah, fantastic. Thank you. Before we turn to the Q&R, I have one thing that I'd like to do is to plug the talk next week. which is by Michael Hoare and myself about LADAL and ATAP. So if you want to know more about LADAL and ATAP, feel free to join the next LADAL webinar meeting. All right, we have one question that was asked to me privately, so I'll ask you. When you're dealing with megacorpora like Globi, for example, and you want to include speaker level variance in your model, how could you do that? Because the problem there is that you have the URL which points to a blog or a website, but you don't know whether that blog or that website or that instance was actually produced by the same author, because different authors could be publishing on that blog.
Yeah, I don't have a clear-cut answer to the question, I have to admit, because, well, the thing is, I'm not sure there is one, right? I mean,
yeah,
one could try and go with URL as much as possible, but yeah, it would not account for guest blogs, you know, or something like this. So the